Pause the video first and read the details given in the question. There is some background given here. And we are given data that has been collected. The first row of the table gives us the variable. So the variable here is the seed color. And the important thing to note here is seed color is a categorical variable. It's not a quantitative variable. The second row gives us counts. We have 321 black seeds, 77 brown, and 31 pale seed. According to the genetics law, the dominant epistasis should lead to a 12:3:1 distribution in F2. So we'll see if the data that we've collected here will give us evidence that goes against this genetic law. Since we are looking for evidence against something, we need to do a hypothesis test. But since the variable here is a categorical variable and we are given counts in each category, we're going to use the chi-squared test. So to do the chi-squared test, we first need to find the chi-squared statistic. The chi-squared statistic is given by this formula. We have the observed counts, that comes from the table, our observations from our experiment, minus the expected count, what we are expecting to be the counts. And that comes from the 12:3:1 proportion. So once we have decided that we use the chi-squared test, the next part is to solve the problem. When it's an evidence test or a significance test, then the first thing we need to do is set up the null and alternative hypothesis. In the previous problem, our null hypothesis was a no difference statement where the counts were expected to be equal, like a 1:1:1. But in this case, we have a specific proportion given here. So we expect the counts to be in the 12:3:1 ratio. So let's try to see how we calculate the expected counts. What are we expecting the counts to be versus what we actually got, which is given in the table. So first let us add up all the numbers, which adds up to 429. That's the total number of seeds that were observed. Now we have to calculate based on the 12:3:1 ratio as to what we expect the counts to be. That is not given to us. We need to first figure out what the expected counts are. So first let's try to understand what the 12:3:1 ratio really means. So first we add up all the numbers, 12 plus 3 plus 1, which is equal to 16. So if there are 16 parts, then the fraction of the black seeds should be the 12 out of 16. So 12 out of 16 should be the fraction of black seeds in any given number of seeds. The fraction or probability that a seed is brown should be 3 out of 16, and the fraction or probability that the seed is pale should be 1 out of 16. So if there are 16 parts, then 12 out of 16 parts must be black, 3 out of 16 parts must be brown, and 1 out of 16 parts must be pale. So this is what helps us set up a null hypothesis. So the null hypothesis assumes that the law is true, which means the proportion of the black seeds is 3/4, which is 12 out of 16. The proportion P2 of the second type of seed, which is the brown seed, is 3 out of 16, and the proportion of the third type of seed, which is the pale seed, is 1 out of 16. Now we've seen in the previous problem that the null hypothesis is what is believed to be true, but the alternative hypothesis can only be said in one way, and that's exactly what a chi-squared test will show or not show, that H naught is not true. So the alternative hypothesis in a chi-squared test is always H naught is not true. In a chi-squared test, we cannot prove anything more specific than that. So the null hypothesis is assuming that the genetic law is true, which means the proportions are what are given by the genetic law, and the alternative hypothesis is what we will be able to prove using the chi-squared test, and that is that the null hypothesis is not true, and that's all that the chi-squared test will do for us. So before we start any hypothesis test, we need to set up the null and alternative hypothesis, which we have, and write it exactly the way that I've given here. And another thing to do is to set your significance level, like we've done before in many other hypothesis tests. The significance level, we can use 0.05, and it can be changed based on what we need, but let's stick with 0.05 for this problem again. Now we need to find the expected counts. So the expected fraction of counts is given by our null hypothesis. But now we need to figure out exactly what the count would be if a total of 429 seeds were collected. Now, based on our null hypothesis, 3/4 of the seeds must be black. According to the genetic law, 3/4 of the seeds must be black. So if we have a total of 429 seeds, 3/4 of 429 must be black. So the of translates to multiplication. So 3/4 times 429 is 321.75. So 321.75 seeds are expected to be black. And note that we have a decimal number and not a whole number here, although we are doing a count, but it's okay to leave it as 321.75. Now the fraction of the brown seeds in a total of 429 must be 3/16. So 3/16 of the 429 seeds must be brown. So the of again translates to multiplication. 3/16 times 429 equals 80.44. Again, leave it as a decimal. 1/16 of the pale seeds, of the total seeds, must be pale. So 1/16 of the total number of seeds is pale. Again, 1/16 times 429 is 26.81, and that would be the expected count of pale seeds. So what we've calculated here are the expected counts. What we are expecting is the null hypothesis, because we always assume that what we are trying to find evidence against is actually true. So the genetic law says that out of 429 seeds, 321.75 must be black, 80.44 must be brown, and 26.81 must be pale. So these are the expected counts. So given a ratio, this is exactly how you would figure out the expected counts that are not usually given in the question. Now this table gives us everything that we have so far. The observed counts are given in the question. So that's 321 black, 77 brown, and 31 pale. The expected counts are calculated based on assuming that the genetic law is true, and that's what we've seen in the previous slide. Now all we have to do is substitute all the numbers into the formula. So observed first minus expected, so 321 is the observed, minus expected, parentheses the whole squared, divided by what is expected, which is 321.75. 77, which is the observed brown seeds minus expected number of brown seeds, square it, divided by the expected count of brown seeds, and the 31 is the observed number of pale seeds minus the expected number of pale seeds, the whole square, divided by the expected number of pale seeds. So we've calculated the chi-squared statistic. It's important to write down each number that you get from your calculation for each category. So we have 0.0017, 0.1471 from the second category, and 0.6548 from the third category. These are called the chi-squared components. These are the components that add up to the chi-squared statistic. So this is the component for the black seed, this is the component for the brown seed, and this is the component for the pale seed. And they add up to 0.8037. And if you've looked at the chi-squared table, a number that is high gives us some hope that we have evidence against the null hypothesis. But a number this low, which means close to zero, is probably not going to give us the evidence against the null hypothesis. However, we need to complete the test to figure out exactly what the p-value is. In order to use the table D, that is the chi-squared distribution table, we first need to figure out the degrees of freedom in order to find the p-value from the table. So the degrees of freedom here is the number of categories or buckets minus 1. Remember that it is not the total number of seeds, it is the number of categories into which we've divided these seeds, and you subtract 1 from it to find the degrees of freedom. Once we have the number of buckets, we know the number of degrees of freedom in this case is 3 categories, black, brown, and pale, so that's a total of 3, minus 1, so that is equal to 2 degrees of freedom. Once we have the degrees of freedom, we know exactly which row to refer to in table D. Sorry, this is not table C, this is table D that we have to look at, which is the chi-squared distribution table. Now that we have our degrees of freedom, which is 2, we go to the table and look for the row headed by 2 degrees of freedom, and we look for our chi-squared statistic, which is approximately equal to 0.80. Now we need to find our number in the table. Now in this case, our chi-squared statistic 0.80 is less than 2.77, which is the lowest chi-squared statistic in the table. The p-value related to 2.77 is 0.25. Our number lies to the left of it, so our p-value must be greater than the p-value related to 2.77, which is 0.25. So the p-value related to our chi-squared statistic, which is 0.80, is greater than the lowest p-value that you see there, because it's further to the left, which means it is closer to 0. So the p-value gets bigger, so that would make it greater than 0.25. And we've set our significance level at 0.05, and clearly 0.25, if a p-value is greater than 0.25, it would have to be greater than 0.05. So our p-value, we can conclude, is greater than 0.05. So the news is that we have no evidence against the null hypothesis. So we fail to reject the null hypothesis. So our conclusion is, based on the chi-squared test alone, that we have no evidence, because our p-value is greater than 0.25. We have no evidence to reject the genetic law that says that the dominant epistasis should lead to 12 to 3 to 1 distribution in F2. So the conclusion of the chi-squared test is that we fail to reject the null hypothesis. We do not have any evidence against it. The minute you say evidence, you got to present the evidence, and it's important to do that in a conclusion. Just write down your p-value, because that's your evidence for or against, depending on what we get. So we do not have any evidence to reject the null hypothesis, which is that the genetic law is true. Now, we follow this up with more analysis of the chi-squared components to make further conclusions, but the chi-squared test can only give us this one conclusion, that we have no evidence against the null hypothesis. Now, we do not have any evidence against the null hypothesis, so let's go and look once again at the data that were given to us and our expected counts that we calculated. And let's see if the counts tell us the same story. So we have 321 black, which was observed, and our expected count was pretty close, which was 321.75. That is very close to what is expected. We look at the brown seeds. The observed number of seeds coming from the table of observations was 77, and what was expected based on the genetic law was 80.44. Again, very close to what is expected. 31 was the pale seeds. That was the observed number of pale seeds in the 429 seeds that we collected. And the expected counts were pretty close, 26.81. So the table also shows, when we compare the observed and the expected counts, the table shows exactly what we got as our result, which is that we have no evidence against the null hypothesis. Our data, which is the first row, kind of agrees with the second row, which is the law that we were trying to get evidence against. So in a chi-squared test, the result of the chi-squared test will only either allow us to reject the null hypothesis or fail to reject the null hypothesis. But if we want to make any further conclusions, we have to do that after we've concluded the test by analyzing the expected counts and the observed counts to see if they were kind of agreeing, or was there a big diversion from the null hypothesis that is expected to be true. So this is only after the test that we can look at the data and make our own conclusions, but the test ends in the step before this analysis. Now, if you're going to use Crunchit, which is on Launchpad, then follow these instructions and you will get results of the test along with the p-values, and then you can make conclusions based on what the software gives us.